What we're going to do today is take a look at things that are called indirect proofs. Basically what an indirect proof is kind of doing it by contradiction. We assume something that is incorrect, and therefore if we say that that is wrong, well, then it must be true. What I want you to make sure that you have down, though, is those 3 steps. Make sure that those go into your little books. So I'll give you a few moments to take care of that. Okay, so the idea is with those steps is assume the conclusion is false. So whatever you're trying to prove, do the opposite. Show the assumption you made is contradicted by a theorem or postulate the definition of the given information. And state that the assumption must be false, so the conclusion must be true. So, if 2 lines intersect, then they intersect at exactly 1 point. Okay? So, if this is what I am trying to prove, well, to disprove it, I'm going to say that, well, instead of exactly at 1 point, I'm going to say exactly at 2. So I've got one line goes through like that, the other line goes through like that. Okay? So I've got my lines. Let me redraw that just a moment. So there we go. I got my 2 lines going through 2 points. Is this true? I just did it. They're lines, right? So is there a rule? Is there a theorem? Is there a postulate? Is there a definition out there that goes and states that, that's not the way it is? First thing would be, what is the definition of a line? How do we define a line? That straight, okay, so we got straight in there, that's good. Connected by 2 points? Well, lines connect points, points don't connect lines. So try that again. There's got to be a rule, a reason, a definition why I can't make this statement. This goes back all the way to September, guys. How do we make a line? 2 points. So that goes back to that rule that through any 2 points, how many lines can I draw? 1. So if I have a line going through, oops, that didn't quite do what I wanted to. So if I've got a line and it is going through those 2 points, that's it, right? That's all it can be. I got a line going through 2 points. That's it, because that's the definition of a line. 2 points define where a line is. You guys ever hear of a globe? Never heard of a globe before. You've never studied latitude and longitude? Never heard of such things? I know you've heard. Where do the lines of longitude intersect, meet? Do they meet? They don't meet. Latitude doesn't meet. Longitude, don't they meet at the poles? But those are called lines of latitude, right? Or correction, longitude. They're lines, but they meet. Well, the reason why that happens is because that's a different type of geometry. We're looking at something that is just simply Euclidean. Cartesian coordinates, just flat. If we we take a look at a sphere, then we have something completely different going on. So this is the idea that you've got to go through and find. You know, what is the rule that states it? In this case, 2 points identify a line. So what I want you to do here is I'm going to give you a few moments, and I want you to go and think about these two things. What is it that you would need to do? So Logan, what would I have to assume if I wanted to use this idea of an indirect proof to show that that wasn't the truth for A? What would I have to do? Well, I want to show that the measure of angle X is equal to the measure of angle Y, correct? So if I'm doing this by a contradiction or an indirect proof and that when I make it false, what would I state then? Well, I want to make that true, right? So what makes it false? What's the opposite of it? Not equal. So that means that I would have to make the statement that the measure of angle X is not equal to the measure of angle Y. Okay. So what about B? What would I have to do there for B? Kevin. Because we're making the assumption that AB is perpendicular to CB, correct? So what would I want to assume then? That it's false. Okay, so what do I have to assume so that it is false? Yeah. So AB is not perpendicular to CB. That's really all that you got to take a look at. Now, if you wanted to, could you go and state that AB was parallel to CB? And that would be true, but the thing is, it doesn't take into account all of the possibilities. Okay? So, let's try this. I want to use the diagram here to prove that theorem 74.2, if an inscribed angle intercepts a semicircle, then it's a right angle. Okay. So we are told that AC is the diameter of M. Okay. So if I cut a circle into half, what does that mean this is in degrees for going around it? Okay, so that's 180 degrees. Okay. Do we have a rule, a theorem, a definition, postulate, something that explains to us the relationship between an angle whose vertex is on the circle and goes out to the edges, like this? Do we have a rule that says something about that? I think we just seen that a couple days ago, didn't we not? What's the relationship between, say, this down here? It's what? Well, I don't know that's 90. I just know that it's an angle measure of X degrees. Okay. I want to know what the relationship between this X here is and this out here in the degree measure of the semicircle. Double, yes. So that's 2x degrees, correct? And that theorem is what? 74 point, or 74-3, or something like that. I can't remember off the top of my head. But you'd be able to go through and write it down, would you not? Yes, no, maybe so. Or 74-1. Anyhow, whatever that theorem is. So we know that we get that from 47-1. So what does that mean that this angle measure down here must be? Yeah, it has to be 90 degrees. So I've gone through and done that. Now I've talked it through. I didn't write as much down, so I could probably say by theorem 47-1, we get that. More often than not, having a picture of what it is that you're talking about is going to be extremely helpful for this. You can probably draw it out and then identify what it is that the rules are. So, I'm going to give you a few moments, and I want you to think about this one and see what needs to be done. So, Keely, can you give me something that I could use to explore this contradiction? Okay, so if I were to draw this out then, so I got myself a triangle here. So I could put a mark here like this and a mark here like this. Would that indicate what you stated? Okay. Is that enough? Is that enough to go and say that, hey, you know, an isosceles triangle has at least two congruent sides? So to prove this statement indirectly, assume an isosceles triangle does not have two congruent sides. So we did that. What do I have to look at? Do I know anything about this side yet? No. Could it be congruent to one of the other two sides? So if I were to go through and put that in, so I've got the marks on there, 1, 2, and 3. Does that indicate that none of the sides are congruent? That's what I'd have to look at. I would have to consider that we have an isosceles triangle that has no sides congruent. Of course, that doesn't work in an isosceles triangle, but let's do it like this. That makes sense? Always are looking for what does not work. So I'm going to give you a few moments, and I want you to think about this one. So Hannah, what could you give me to use so that I can do an indirect proof here on this one? What would be a piece of information you want? Okay. So if I draw a triangle, it looks like this, but it says at most. Okay, so that means that this would have to be 0. Okay, so we got 0. Would that work for us? A triangle can have at most. But I made a triangle, right? So can I make a triangle with 0 right angles? Okay. So this is 0. What would happen if I tried this? Can I make a triangle with 1 right angle? Let's try 2. Okay, so here's 1 right angle and here is another right angle. Do I have a triangle? Could I extend this out and try and get them to bend together so that they would have that? No. So, okay, I've got one thing there. I tried to make a 3-sided figure that had 2 right angles in it. So starting with 0, then moving up to 1, then moving up to 2. Good. Is there another way that I could have considered this? Parker, did you do it this way? Okay. Did anybody not do it this way? Yes, sir. What did you do? Okay. Well, what did you write? That they what? Oh, I got a triangle there with 1 right angle. Why? Okay. How many degrees does a triangle have to add up to? So this could add up to 180 degrees, right? This here, with this being 90 degrees here, can still add up to 180 degrees, right? Now, a triangle has to have three angles, correct? But if this is 90 degrees here, this is 90 degrees over here, that's already 180 degrees. What about the third angle? So if the third angle isn't there, do I have a triangle? Well, so there you go. There's another way of looking at it, that the sum of the angles is 180 degrees. Two right angles is 180 degrees. Don't have a third angle. Can't do it. So what about this one? I want to go and prove that a right angle is always going to be the shortest distance between a point to a line. Now we're told that that's perpendicular, correct? So what would I have to assume? Well, I would have to assume that not a perpendicular line. So if I think of not a perpendicular segment, okay, that means I could have a point sitting over here, correct? Over here, correct, right? Over here or over here at C or whatever it is. I could call that E, I could call that F, I could call that G. Now, I want to go back and just think about what I see here. What kind of a triangle is that? What do we know about right triangles? 90 degrees. What else do we know about triangles? Or especially right triangles? Hmm? Pythagorean theorem. A squared plus B squared is equal to C squared, right? So, the distance that we would be looking at for the line would always be the hypotenuse, right? So that means it would have to be A squared plus B squared is equal to, is equal to C squared, okay? Where B is the perpendicular line, correct? Now, when I had the lines that I was drawing out here that I wanted to say E, or I wanted to say F, or I want to say G, could I make right triangles with A and B all the time? Mm-hmm. And since these add up to C, which is the distance here, would B always have to be less than C? Would that always have to be the case? Because if I'm adding something to B squared to get to C squared, can B and C be equal? So there we go. That tells us that the only way for this to work, because this is a perpendicular line, this is a leg, that is a leg, this is the hypotenuse. Two legs always add up to the hypotenuse. So any other point that would be on the line would have to have this distance here being greater than B in order for this right triangle to be there. There we go. So, okay, we give you a couple minutes and I want you to think about this one. So, Miss Anderson, what would I have to assume here to make this work? Miss Anderson, your voice has changed. Your voice is a little deeper than normal, Miss Anderson. Must have been all that singing yesterday, right? So, what would I have to assume Okay, so absolutely correct. So M is not parallel to N. Okay. So if that is the truth, how in the world could we get that they're supposed to be equal? Any thoughts on that one? A little trickier, isn't it? So let's try this. Well, let's also assume that angle 4 is not congruent to angle 6. Oops. Angle 4 is not congruent to angle 6. Now remember, when they say this, that means that the conclusion is false, not the information that they give us. So by starting out that M was not parallel to N won't quite get us there. Okay. So it's a good way to start things off, maybe, to consider that option, but we don't want that. Because if I have M and N parallel, what does angle 6 plus angle 3 add up to? 1? 9? No. Angle 6 is a label. Angle 3 is a label. 6 plus 3 do not give us 9. We're talking degree measure here, partner. So, how many degrees do 6 and 3 have to add up to? It's one of the rules that we have. 180? Yeah. 180. 180, because these are the same side interior angles. Okay. What does angle 4 plus angle 3 add up to? 180 degrees. Why? What are they to each other? Corresponding angles. Not corresponding angles, but supplementary angles. So, does that mean that angle 6 is equal to angle 4? Isn't that one by transitivity? Wouldn't that, I shouldn't use transitivity, I should use substitution. Okay. So if I substitute, I can substitute in 6 and 4 and I still get 180 when added to 3, correct? There we go. So if we assume that they weren't parallel to begin with, I wouldn't have been able to use the same side interior angles because that only works if lines are parallel. So if I assume that 4 and 6 aren't congruent to begin with, there we go. Now, could have I just gone through and said, hey, you know what? 4 and 6 have to be the same because of alternate interior angles. Would that even been quicker? Yeah. It all depends upon what rules you see. So this will be due at the end of class on Monday.